Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to today's webinar, Underground Stormwater Storage for Detention or Reuse. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures, and to elders past and present. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, ECHO. ECHO in Australia offers an extensive portfolio of stormwater, building draining systems, cable pit and ducting systems, access covers, and other niche products. ECHO takes pride in providing excellent customer service and extensive technical support from specification to the finished product installation. Today's session will feature two speakers, followed by a live audience Q&A. And as always, I encourage you to send questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Anthony Healy. Anthony is a civil and structural engineering consultant specialising in end-to-end design and delivery of commercial and industrial developments. Areas of expertise include water-sensitive urban design, stormwater drainage, portal frame structures, and cold-formed systems. Please welcome Anthony Healy.
Good afternoon, everyone. My name is Anthony Healy. I am a Senior Engineer and Director at Eclipse Consulting Engineers. Eclipse specialises in civil and structural engineering of commercial and industrial developments from concept through to construction. We've delivered hundreds of projects up and down the east coast of Australia, and in the last 10 years, the vast majority have included some form of stormwater storage as part of the design brief. The design of below ground tanks, specifically for water storage, is relatively straightforward. But there are a handful of key procedures which, if not properly considered, can lead to premature failure of the system. In today's presentation, I'm going to briefly touch on why we might want to harvest stormwater underground. I'll also talk about common construction techniques in the industry used to achieve this, as well as addressing specific structural considerations for below ground tanks. This brings me to my first question. Why store stormwater? For most new developments, there are three main reasons to intercept stormwater before it leaves the site. The first is to capture it for reuse. This may include rainwater tanks directly connected to roof drainage lines, which, if properly treated, can be used as a source of potable water. It's also possible to store stormwater from hard stand surfaces, but this is generally only used for landscaping irrigation and specialised industrial applications. The second reason we might want to store stormwater is for an improvement in stormwater quality. While this does have some overlap with capture of stormwater for reuse, there are two primary mechanisms by which pollutants in stormwater can be prevented from entering downstream waters. The first is self-evident, and that's in recycling the captured water. By reusing captured water, we can prevent pollutants from ever leaving the site as surface pollutants. That said, if the reused water ends up in the sewer system through internal reuse systems such as washing machines or toilets, this isn't an end-to-end loop of pollutant capture. The same can be said for landscape irrigation, where residual pollutants may end up in groundwater systems. The other mechanism for pollutant removal is sedimentation and settling. This mechanism is common in systems such as rainwater tanks, where long residence times allow gross pollutants and sediments to settle to the bottom of the tank, as well as specially designed systems such as temporary or permanent sedimentation basins. And as you can see on the slide, we have an example of a temporary sediment basin which is currently under construction on a site in Somersby, New South Wales. The third reason we might want to store stormwater is for stormwater detention, And as suggested by the name, stormwater detention is about detaining water temporarily before allowing it to discharge downstream. Now, why would this be something that we're interested in doing? Well, the process of urbanisation of rural and undeveloped areas has resulted in catchments that were previously pervious, which means that they have the ability to absorb water directly into the ground, becoming impervious, meaning that rainwater on roofs, driveways and roads becomes runoff, which discharges directly into creeks and rivers. The main impact of this is that in large rainfall events, you get a large spike in the volume of runoff coming off these urban areas, where previously the catchment's ability to absorb the water mitigated most of this impact. The effect of this high speed, high volume of stormwater is erosion of creeks and riverbeds, as well as flooding, but also particularly flash flooding. Stormwater detention is a common way to deal with this. By intercepting stormwater and forcing it into a storage system with a small outlet at the bottom, we can force stormwater to be slowly released from our new development. Most of the time, the goal is to be at or below the peak discharge rate from the pre-development scenario, to ensure that the maximum flow of water leaving the site is lower than the worst case if the site was still entirely pervious. It's worth noting that even when we control the rate of water discharging from our site, we still end up with a larger volume of stormwater overall, which is the area under the curve in this diagram. This is part of the reason why capturing stormwater for reuse is particularly important in ensuring that we aren't keeping creeks and rivers wet for too long after each rainfall event, remembering that our goal is to mimic the natural water cycle as much as possible. For most commercial and industrial developments, local councils will require what is known as on-site detention, or OSD. In essence, this is a detention system which is constructed within the site boundary to capture stormwater before it is discharged to council's local drainage system. For residential developments, this tends to be provided at a subdivision level, with a single basin or a tank provided at the downstream end of the catchment rather than a detention system for individual lots. There are a couple of ways we can determine what shape and size our detention system needs to be. If we're talking really rough numbers, if you assume that your tank is about 1 meter deep, the tank's footprint is generally no more than 3% of the site area. This is for developments where the impervious area is around 80 to 90% of the total site area, which most industrial and commercial developments are. Here are some examples of some tanks that we've designed in the last year or so in the Central Coast and Newcastle area, and these are all in the 2 to 2.5% footprint range. Obviously, detention design tends to be a little bit more detailed than this, and there are a couple of techniques that are acceptable in accurately determining appropriate detention volume for a given site. The first is a first principles calculation. We can figure out what depth of rainfall is going to fall within a given time frame, and we can then multiply that by our catchment area to get our volume. And then we can size the orifice based on restricting the flow to pre-development rates. In Australia, the Bureau of Meteorology provides synthesised rainfall data, which can be used for the simulation of storm events. This information really is the gold standard when it comes to assessing critical storms in detention design. This data that we have access to allows us to use runoff routing software, including Drains, XP Rafts, and InfoWorks ICM, to simulate both drainage networks and detention tanks with multiple stages and ensure that storage volumes are optimized. These systems tend to be fairly common in industrial and commercial development design. Before moving on to the next section, I do want to touch briefly on below ground infiltration systems. These are effectively detention tanks, but instead of using an orifice to control the discharge rate, you are using a portion of the bottom of the tank to allow water to soak directly into the ground. There are a couple of extra considerations to take into account before designing these. Firstly, the ability of water to infiltrate into the ground increases linearly with tank area, and they often need to be quite large in order to be able to store enough water for your very large storm events. The other thing to take into consideration is the condition of the soil on the site, as this will greatly influence the ability of water to soak away. It's important that the site's infiltration capacity is investigated accurately and thoroughly on site by an expert. Infiltration tanks can end up taking 20% of the site area in order to function safely. And as such, they really should only be considered as a last resort where other options are not feasible. So let's move on to talk about our options for stormwater storage as designers. There are three main options available for below ground stormwater detention tanks. Each have their own quirks, advantages and disadvantages, and I'll touch on each one briefly in this section. The first is in situ concrete tanks. These are by far the most common tank type, and for most of our designs, this consists of a reinforced concrete base slab, core-filled reinforced blockwork walls, and a suspended concrete slab for the lid. Builders find them fairly easy to build, particularly where concrete slabs and blockwork walls are already being installed as part of the contract for the rest of the development site. In recent years, we've seen some builders opting to use permanent formwork concrete walls, including ready wall and rise wall as an alternative to blockwork walls, but this generally has a negligible impact on the design itself. For the tank lid, we typically see a preference for Bondec permanent formwork due to the ease of install over traditionally formed temporary formwork systems. The second option that we have is precast tanks. Precast tanks are an alternative to cast in situ systems, which have the advantage of being able to be installed much more rapidly. You're effectively able to dig a hole, drop in your tanks and then backfill, which can be a significant time saving on site. There's also the added advantage of not needing form workers, steel fixers and concreters if they're not required for other aspects of the job. We are seeing an increase in the popularity of precast systems in Australia, particularly for larger projects where time comes as a premium. Our third option is geocellular tanks, which are specialised plastic crates used to form below ground voids for the storage of stormwater. In Australia, the popular options are generally provided by Atlantis, ACO and Ausdrain. The plastic crate system vary from supplier to supplier, but are all based on the same principle. As plastic does not have the same structural strength as concrete, the voids in geocellular tanks are usually significantly smaller and they're not often big enough for a person to access them. However, the use of plastic crates over concrete results in a substantial increase in the ease of installation. The crates are very small and light enough to be installed by hand without craneage in a very short time span. The plastic material is also often recycled, which reduces your project's carbon impact. And if designed correctly, the structural performance of geocellular tanks is equivalent to concrete. Now that we've had a brief introduction to each type of system, let's draw some comparisons. On this slide, we've got 4 categories where a comparison can be easily made between each system, but it's by no means exhaustive. The first is install speed. Geocellular and precast systems are clear winners here, as there's no need to wait for concrete to cure or the need for specialist contractors. Under maintenance access, in situ and precast are both the preference. Even though inspection and maintenance of below ground tanks generally requires entry to a confined space, a maintenance contractor can physically get into the tank and make repairs or clean components as needed. For geocellular tanks, generally maintenance is limited to what can be achieved using a CCTV camera and a high pressure hose on a snake. Similarly, for hydraulics and stormwater treatment, if you want to put weirs, orifice plates or stormwater treatment cartridges inside your tank as part of the design, you have infinite flexibility with in situ tanks. This is mostly achievable with precast tanks, but sometimes you are limited to the geometry of the precast modules. For geocellular tanks, any stormwater hydraulic or treatment devices must be contained separately in manholes or pits upstream and downstream of your detention tank. Finally, on sites where you're limited for space or need to integrate the detention tank into the walls or foundation of the building itself, in situ tends to be the only practical option. Precast might be an option if you have the engineering support from the supplier, but geocellular only tends to be an option in dedicated open spaces or below parking and driveways. The important thing to remember is that these comparisons are not hard and fast for every single development, and as engineers, the value that we can provide for the client lies in being able to identify which option is going to provide the best outcome for your stakeholders. So for the final section of this presentation, I'm going to talk briefly about some structural considerations. Being both a civil and structural engineer, I have a lot of experience in designing below ground tanks both hydraulically to ensure that they actually meet stormwater performance requirements, and structurally, making sure that they are both practical to build and can withstand the loads that it will be subject to during its operational lifespan. For an in situ tank, I'm going to work from the bottom to the top and talk about some of the structural considerations that need to be made at each step. So starting with the base slab of a detention tank acts as your foundation. The design will generally be informed by the advice of your geotechnical engineer, but there are a couple of important questions to ask for every development. The first question is the foundation going to be subject to subsidence, groundwater, or highly reactive soils? And your second question is, are there existing services that need to be protected from the additional load of the detention tank? I have on the slide at the moment an example of a development in Albion Park, New South Wales, where an existing sewer line was to be removed, then replaced and concrete encased below the detention tank. We needed to design a detention tank foundation system that would ensure that the loads from the tank were not transferred to the sewer line, which involved piering below its zone of influence. Next up is the walls of our tank. The side walls of your tank transfer force vertically from the tank lid to the tank base, but they will also be subject to lateral loads from both earth pressure and internal and external water pressure. This said, it is not necessarily required that these walls are designed as a retaining system in conjunction with the base slab. If designed correctly, the walls can act as a simply supported vertical spanning element between the base slab and the top slab. A couple of key tips for tank walls. Firstly, ensure that adequate subsoil drainage is provided before you backfill. Even if your soil is perfectly dry and never subject to groundwater, blockwork bricks are porous. And in detention tanks, water from inside the tank may leak into the soil outside, and this water needs to be given the ability to drain without building pressure on the wall. Secondly, if the tank is being used to store water permanently, as may be the case for rainwater, be sure that adequate waterproofing measures are designed to ensure that leaks are minimized. Finally, for our top slab, as I mentioned previously, these are typically Bondec or an equivalent. For me, the main consideration for Bondec is that, unlike interior environments, the Bondec slab in a detention tank is subject to constant high humidity, which will eventually cause the Bondec formwork to completely rust away. As a result, the bottom reinforcement in the slab must be designed without the influence of the Bondec. The other things that can make or break your top slab is your vehicular loads. In a lot of cases, it's easy to put a detention tank under parking spaces and claim that it will only ever be subject to Class B or Class C vehicular loads, but you might be caught out if the parking spaces are unoccupied and a truck driver decides to use the space to do a 3-point turn. Another area where it's easy to get caught out is on industrial sites where forklifts may be present. Forklifts often exceed Class D loads and may be as high as Class E in some heavy-duty applications. It's critical that both slabs and access hatches are designed for the appropriate loads that may be encountered on the site. On this note, I do want to touch briefly on access for maintenance. On top of minimum access requirements for confined spaces, make sure that you have at least one access for every individual chamber and that step irons are installed for deeper tanks. Make sure that your access hatches are large enough to get both people and equipment in and out of the tank easily, making sure not to forget about stormwater treatment cartridges where applicable, which will need to be lifted in and out of the tank during maintenance and swap out periods. For our precast or geocellular tanks, a lot of the design information that is available comes directly from the manufacturer or supplier of the system. On the screen at the moment, I have a worked example of ACCO's online structural calculator for their Stormbricks system. As engineers, ideally what we're looking for is a system that has testing data available, and that data proves that the system can withstand the loads that it may be subjected to. On top of this, we want to see a robust installation methodology, which can ensure that the advertised performance can be met on any site, provided that it is installed correctly. This is all I've got time for today, but I look forward to answering your questions during the Q&A. Thank you.
I'd now like to welcome our second and final speaker, Kate Jennings. Kate is the specification representative at ECHO, overseeing projects across New South Wales and the ACT. She works closely with engineers, architects and hydraulic engineers, offering free project consultations to help deliver effective drainage and infrastructure solutions. In addition to supporting projects, Kate also facilitates CPD events and product presentations to keep industry professionals informed and up to date. She is dedicated to providing innovative products, technical expertise, and practical tools that support the success of every project. Please welcome Kate Jennings.
Thanks, Amanda, and good afternoon and welcome to our presentation on underground stormwater storage. Before I start, I'd like to thank Anthony from Eclipse Consulting for presenting alongside me, and also to the EA team for their help in making today's webinar possible. So in today's presentation, I'm going to describe the role of geocellular underground plastic storage tanks, their characteristics, and give some guidance on how to specify them for the best design outcome, and touch on the cost benefits of a well-designed and integrated plastic tank compared to concrete. Underground tanks are used in many projects as councils want to protect their downstream waterways and infrastructure from rapid runoff from our urban developments. Managing the quality and quantity and speed of water being discharged from a site is only going to grow in importance as our cities urbanise and create more impermeable surfaces and as rainfall events intensify. In-ground tanks are a conventional way to store and slow down the surface water runoff back to pre-development rates, as well as replenish the groundwater at a more natural rate. And designers do this by firstly collecting stormwater in a drainage channel, cleaning it with some kind of pretreatment to prevent clogging or contamination downstream, holding and then releasing into the stormwater system to emulate the natural water cycle. And there are a number of tank options available to engineers and urban designers, which could be either natural or engineered structures. So from the top, detention basins are one option. You see these used often in low to medium density areas as they take up land that otherwise could be used for urban or commercial developments. The next is precast or cast in situ concrete tanks. These are typically expensive to construct and transport, and I'll talk more about the costs of concrete tanks later on in the presentation. Next along are plastic arch systems, which require a pretty decent amount of space to install. And lastly, plastic tanks. And within this category, there's a huge range of different options, with not all being equal. And this will be the focus of today's presentation. Plastic tanks could be milk crate style systems or open cell geocellular structures. And these tanks can be used for detention, retention, or infiltration. So detention systems are designed to spread the peak flow of a storm event. It does this by releasing stormwater slowly to control the runoff and reduce the risk of flooding downstream. This slow release of water is typically managed with an orifice plate that's located downstream of the tank. A retention system collects and stores water permanently for reuse. So, for example, to water landscaped areas or for firefighting purposes. And actually, I'll share a really innovative case study later on from a project in the Blue Mountains that I worked on. Infiltration systems are used mainly in sandy areas to temporarily store water and allow it to seep back into the ground to replenish a dropping water table. Now, depending on which type of system is being used, the wrapping needs to change for plastic tanks. In a non-sensitive retention or detention application, and by this I mean where the tank isn't located close to a building or doesn't have contaminated soils, for example, a taped geomembrane system with geotextile can be used as the ground conditions can accept minor leakages from the tank. This methodology is used in the vast majority of applications. But for sensitive retention or detention applications, so for example, if the tank is located very close to a building, we'd recommend using a welded geomembrane that's installed by a specialist plastic welding contractor to really make sure that the system is watertight. Then the geotextile wrapping over the top of the tank would be taped, and this geotextile is to protect the membrane. And for infiltration systems, here there's no membrane used, just a geotextile to minimize the sediment buildup within the infiltration system itself and minimize the fines entering the tank. Geocellular plastic tanks can be suitable for many projects like car parks, driveways, landscaped areas, commercial buildings, schools, industrial areas, airports, and military bases. And as I mentioned earlier, there are a number of elements to consider when selecting plastic tanks. And in the industry, there's a really wide range of plastic tanks. And of course, they're not all created equal. The two on the bottom of the screen are typical of plastic crates, and the one on the top is typical of a modern geocellular unit. Unlike concrete tanks, plastic tanks are versatile. So they can be cut and joined, and the structure can also be used for infiltration. Well-designed plastic geocellular tanks have a high void ratio and they're easily maintained. Good designs are load rated and they hold their strength over time, but there are poorly designed plastic tanks that are difficult to access, inspect, and maintain. And unfortunately, that can give plastic tanks a bad name. So it's important to know what to look for. We suggest 5 key things to consider as a designer when you're selecting a geocellular stormwater tank. So the strength and the loading, the tank layout, the hydraulic capacity of the tank, assembly and installation time, and accessibility for maintenance. So first, strength and loading. So with any product, of course, compliance to legislation and standards is critical to make sure that a product's going to perform as it should. The council's design specification will specify what methods an engineer needs to use to show that the property meets the council's stormwater management requirements. So this takes into account the volume of water that the property needs to capture, store, and detain from both the landscaped and roofed areas. Stormwater storage tanks have to be designed into a project by a certified engineer, and any products have to be quality assured. Now, in Australia, there's no standard that governs these types of geocellular tanks. And the problem with that is that some manufacturers make claims about strength and design life that just aren't substantiated by compliance to a standard. Syria is a British standard and is specifically written around geocellular tanks and guides on testing, structural design, construction, and installation. And in this standard, there were 4 main factors that were identified as contributing to failures. So an inadequate design and not taking into account the ground conditions, a lack of understanding of a particular tank's performance and therefore overloading the tank, not considering the influence of groundwater, and inappropriate test methods that overestimate a unit's strength. So this is a dominant industry standard and it's ideal to benchmark performance. And as such, manufacturers and suppliers in Australia should show compliance to this standard to ensure that failures don't occur and a good design life is maintained. Understanding the strength of a tank is absolutely crucial to ensure it can bear the loads it will be subjected to. And the greater the structural strength of a system, the shallower it can be buried. So designs that offer a reduced level of cover enable shallower excavations and reduces construction costs as a result. What determines the depth of cover required are things like the soil type, vertical loading, groundwater levels, and the surface finish. And when we're considering loads, both short-term loads and long-term loads must be considered. Some manufacturers and suppliers will only market the short-term strength of tanks, and the long-term loads can be overlooked, but obviously crucial for a long installation. Products need to be able to hold the weight constantly over a long period of time. And as plastics are liable to creep, meaning they deflect over time, products need to be strong enough to withstand this. And the consequences of failure can be quite extreme. And this image at the bottom of the screen is an example of an installation failure where the tank failed because of creep. This picture is really every designer's fear with stormwater storage tanks and just highlights the importance of a structurally sound and load-rated tank. And here's another photo. It's not actually a sinkhole, but a catastrophic tank failure in Pittsburgh in the US. Short-term loads that should be considered are dead loads. So like the mass of soil surrounding the structure plus the weight of slabs or anything else permanent that the tank will be subjected to. Live loads are temporary loads like vehicles, which also need to be considered. Tanks that have vertically aligned load-bearing pillars will offer good vertical strength and stability, and manufacturers should be able to provide you with independently tested vertical load results. Lateral loading is as important as vertical loading and takes into consideration soil mechanics. And this is the key driver for how deep a tank can be installed. In high water tables, tanks can be pushed out of the ground because of buoyancy. So in these instances, we want to either locate the tank close to the surface to avoid the water table or beneath a heavy pavement to anchor it down. Choosing a tank that can be brick and cross-bonded allows for a more rigid tank construction. So rather than having independent cells, this methodology allows for a completely connected layer for more stability. And again, manufacturers should provide independently tested and certified lateral load data. And this is to justify the installation depths that they recommend for your project. So there's heaps of lab tests that can help manufacturers and designers, but taking a tank out of a controlled environment like a laboratory and measuring its behavior in a typical environment gives us a better indication of its performance. So we conducted a full-scale live load test on a buried tank, which was documented by Ohio University. And we did this by installing a 3-layer tank with a compacted soil and asphalt surface, which was then trafficked by a 27-ton water truck. But first, the installation. So the excavation is dug and the foundation leveled. The tank is then assembled within the excavation and on top of the membrane layers, and the sensors start to get installed to measure vertical deflection. The tank is then wrapped with a geomembrane. And after that's completed, pressure cells are placed around the tank to detect any lateral movement. And then the final installation step is backfilling the tank, leveling and compacting the cover, and then rolling asphalt over the surface to install the tank as it would be in practice. And then the final step was to bring in the 27-ton water truck and complete the testing using a combination of driving over the buried tank and also parking on top of the tank. And Ohio University analysed this data and they wrote a report on their findings. And we'll send you the links to this later on so that you can read it should you want to. So if loads is something that you're interested in diving more into, we've teamed up with Engineers Australia to detail everything you need to know, and we'll also send you the link to this too. The next element to consider during specification is the layout of the tank. A benefit of using geocellular tanks is the ability to make all kinds of weird and wonderful shapes if they're required, to get the tank to integrate with existing infrastructure like buildings or roads. And you get this flexibility by using half tank layers for restricted depth applications, and they can also be cut. I would say, though, that for detention and retention tanks, a rectangular shape is the easiest for wrapping purposes because of the membrane, but the combination of full and half layers means there's added flexibility to hopefully get the layout to work in a more traditional shape. Next up, the hydraulic capacity of tanks is of course critical. And choosing products with a high void ratio helps to reduce the size of the excavation required, and obviously the construction costs are lower because of that. So the hydraulic capacity of a tank refers to the volume of water that a structure can store, and different tanks in the industry will of course offer different capacities. Geocellular tanks have a void ratios of 90% plus, where arch systems, for example, have a void ratio of around 50%, which essentially means that the excavation needs to be twice the size. And the reason for that is that arches hold the water in the open space within the arch, as well as the voids between the aggregate fill that surrounds the tank. And this just isn't an efficient way to hold water, and the aggregate also adds a fairly significant construction cost too. Let's look at concrete structures. So although concrete tanks provide 100% water storage inside the tank, they do have those thick walls, which reduces the void ratio to around 80%. Concrete pipes are obviously round, but they need a square trench. Each pipe also needs about 250 millimeters of sand or stone bedding and around half a meter space between each run. So all of this increases the excavation that's required and the fill, making the installation bigger and more expensive. And the speed of installing tanks is such a crucial consideration, as tanks are often the first thing to be installed on a project, and downtime means that it affects the ability to continue with construction on the site. So again, looking at some different tank options in the market, concrete tanks, arches and pipes, they're all pretty big. They require dedicated storage space on site. In situ concrete tanks are time consuming to install, and there's the downtime waiting for the concrete to cure as well. Plastic crate systems may have to be assembled actually off-site and transported back to site once they're ready to install. So there are additional freight and possibly rent costs associated with building the tanks, whereas geocellular structures are really advantageous on sites without much space. These are really lightweight. They don't require any specialist lifting equipment to install, so it all makes for a very quick and easy installation. Some designs have this simple egg carton kind of stacking design, so they just come off the pallet, connect together, but crate systems are really time consuming to install. And this video is really just showing the speed of Stormbricks versus a traditional crate system. So on the right is my colleague Darren building a Stormbricks unit in the brick bonding method. And on the left, he's assembling a crate flat pack style unit. You might recognize Darren from previous EA webinars, and he'll also be joining us for the Q&A later on in today's session. So here we are. Darren's looking pretty smug because he's finished already with his Stormbricks installation. So you'll see that with a single Stormbrick cell, it's actually got 3 times the capacity of a double crate system, so substantially less capacity and significantly more time to assemble. And to assemble 2 near identical tanks in terms of volume, it would be 200 cells of Stormbricks versus 540 crates. And based on the time that it would take to assemble, Stormbricks, as a large part that clips together fast, could be assembled in 1 hour and 23 minutes. But for the same size crate system, it would take 29 hours and 15 units because of the flat pack nature of assembling those crates. And the last element to consider is accessibility and maintenance, because ultimately we want assets that can continue to have a long working life. Critical to good maintenance is actually having access into the system and making it easy to access the system. A failure to maintain any stormwater tank will result in a reduced capacity and reduced effectiveness of the system. So to get into this tank, an inspection chamber is helpful as it gives us a dedicated access point for both the inspection and cleaning. So this plate is located where layer pieces are removed beneath to allow for access and maintenance within the structure. And again, not all tanks are created equal. Some systems are easier to inspect and maintain than others. Crate systems have that closed-in structure, so you can't actually access beyond that one crate that might have an access unit. Now, historically, councils have preferred concrete tanks to physically send maintenance teams into the tank. But in today's technological age, being in a dark, wet, enclosed space isn't a risk that needs to be taken because we can use rodding equipment and cameras to inspect and clean the tank instead. And here's just a short video showing you how a camera was used to inspect a Stormbricks installation under a pedestrian precinct. So you can see the camera here moving very easily through the system. So it's not restricted by any physical barriers. Those vertical load-bearing pillars allow the camera to move freely through. In the Australian market, plastic tanks are increasingly becoming a more common inclusion in project designs because of the benefits that we've spoken about today. But we do still see a fair amount of traditional concrete tanks within the construction industry. They are becoming less common though, because sustainability objectives are driving the use of alternative materials like plastics, but also because of the cost. So concrete tanks are expensive to install in comparison with geocellular tanks. Ryder Levitt Bucknell, quantity surveyor, carried out an independent in-ground stormwater tank cost comparison, which itemized the site preparation works like excavation, compaction, backfilling, and disposal of excess material, and the product supply cost, which includes the hire of any lifting machinery, such as mobile crane hire for the heavy concrete tank components. And this comparison looks at the Stormbricks tank against two types of modular concrete tanks. And the results show that for the same size tank, for the same site, the modular concrete tank is 56% more expensive, and the modular cylindrical pipe concrete tank is 148% more expensive compared to a Stormbricks tank. The report also looked at another scenario comparing the Stormbricks tank against smaller precast concrete tanks that can be delivered to site on the back of a truck. The results show that the precast concrete tank is 22% more expensive when compared to the Stormbricks tank. And the final scenario in the report compares the Stormbricks tank against a cast in situ concrete tank. And these results show that the cast in situ tank is 62% more expensive when compared to Stormbricks. Cast in situ tanks, they're really labour intensive. They require 28 days as well for the concrete to reach its compressive strength. And just to wrap up, I'll touch briefly on ACCO's products and services to end my presentation today. So a little bit about ACCO, in case you're hearing about us for the first time today. We're a family-owned German company with a worldwide presence, but here in Australia, where I am now, we're headquartered in Western Sydney, where we manufacture many of our products. And we also have offices and distribution centres around the country. For external applications, we have a wide range of graded trench drains for buildings, urban and civil projects, as well as access covers, cable pits, and of course, the Stormbricks in-ground tanks that we've been talking about today. And we have two versions of Stormbricks: SD, which is standard duty for vehicles up to 9 tonnes, and HD, which is heavy duty for vehicles up to 30 tonne. Stormbricks can also be incorporated into water-sensitive urban designs using the Storm Updated program by Clean Stormwater or Music by eWater. Now, Stormbricks is super straightforward. There are only 3 main components of the Stormbricks system: the body, the top covers, and the side panels. All of these are manufactured from a tough and corrosion-resistant polypropylene. The side panels just click onto the perimeter of the tank for lateral support, and the top covers are placed on the top of the tank to ensure consistent vertical support for the cover fill material. ACCO Stormbricks benefits as well from a patented brick and cross bonding feature, which provides unparalleled stability in the construction of the tank. And these load-bearing pillars precisely align one above the other so that loads are really evenly distributed downwards. Cross bonding, which is shown on the left of the screen, crosses modules at 90 degrees to each other, where brick bonding is like laying bricks for a wall, where the bottom two bricks have another brick spanning their joint. And installing our tanks using this methodology just gives a really strong and integrated installation. And here's some case studies of some projects that where Stormbricks has been installed in New South Wales and ACT, as they're the markets that I work in. So this project was a relatively large detention tank in Narrabundah in the ACT. You can see here a taped prefabricated membrane is being used before the top membrane and geotextile is applied. A prefabricated membrane is a fantastic way to minimize the amount of joints required on the membrane, as the only taping or on-site welding that's required is for the top piece. Meek Street in Randwick was a detention tank used beneath a pedestrian precinct, and this one was specified by Randwick City Council. And Bondi, of course, being by the ocean, is a great candidate for an infiltration tank, and the access points make it really easy to maintain. And this was a project for Waverley Council. And lastly, the case study that I mentioned right at the beginning of the presentation, this was with the Blue Mountains Planetary Health Initiative, where a 153 cubic metre retention tank was used for firefighting water storage and to feed the sprinklers on the building itself. This is such an innovative project and so worth checking out. At ACCO, we love working directly with engineers, and we have a dedicated specification team nationwide. Please do get in touch with your local rep. We'd be so delighted to meet with you. Christian and Darren work in our technical services team, and they support us as a specification team, but also our customers, of course. So they work across all of ACCO's products, and for Stormbricks provide assistance with structural calculations and a fully documented proposal that's specific to your project. So this is a service that's offered free of charge and without obligation. And we also have some free online tools that are available at any time for you to use. The first is our online Stormbricks configurator program, and this is to help you specify the right size tank. So all you need to do is provide some basic information like your desired tank size or storage volume, the cover depth over the tank, the type and location of inlets and outlets, and the configurator does the rest. The results can be downloaded, and they give you a summary of all of the inputs, a bill of materials for the tank, and then that's easy to send to our sales teams for pricing and availability. And to make the structural validations process easier, we've also developed a simple online structural calculator. It's really easy to use, and the inputs include the cover depth that you want to achieve, the height of the water table, live loads, the pavement type, and the soil type. And this is all validated by that Syria standard that I mentioned earlier, and provides a downloadable report to advise whether the cover height is suitable for your specific project. Thank you so much for your time today. We'll send you an email after today's event with links to all of the information and programs we've discussed, and also the contact details for your local specification team. I'll now hand you back over to Amanda.
Thank you. Thank you to Anthony and Kate for two great presentations. Before we head into the next part of the webinar, I'm pleased to let you know that we're now joined by Darren Chan, Brand Manager at ACCO. Darren is the Brand Manager at ACCO for Civil Construction Products and the NATO Authorised Representative for ACCO's Testing Laboratory at ACCO, who continue to support engineers and designers with innovative products and free online design tools. It's now your turn to get involved, and we have set up a short poll before the Q&A, as it's great to know what you're thinking right now, and I encourage you to get involved. So if you please can scan the QR code on your screen or follow the link in the description box, the results will be shown on your screen as you answer. We've got 4 questions, so I'll kick off with question 1. And the question is, in the past, what concerns have you experienced most when specifying tanks? Number 1, is there room to fit the tank without interfering with footings, services, etc.? Is the tank strong enough? Is the tank able to be maintained? And is the tank economical to install? Vote now. So as the results are coming through, Darren, I might ask you to comment.
Yeah, just had a quick look at those results, and yeah, all four of those concerns are what engineers and designers deal with every day to make sure they meet the asset owners and or the clients' design brief. Yeah, is this tank strong enough? Is it interfering with footing? So that's structurally, that's probably a concern for the engineer to make sure they design something that's going to be able to be there for a long time and withstand all the loads through its life. For the asset owner, they're probably more want to know how it's going to be easily maintained so they can keep it functioning during its life. And of course, the economics, they want a cost-effective solution. So, those are, I suppose, concerns for all stakeholders.
Thanks, Darren. Thank you for that. Moving on to our second question, and the question is, in your current or past roles, for what purpose have you specified underground stormwater storage tanks, ranking 1 to 3, with 1 being the most common? Detention, infiltration into surrounding soils, retention, reusing the water for other purposes. Vote now. So Darren, if you'd like to just comment on that.
Oh, look, with more new developments, there needs to be incorporated a stormwater tank, whether it's detention, infiltration, retention. Usually with new developments, councils will have in their DA requirements what kind of detention tank, what size detention tank, and I suppose the flow rate that you can put back into the stormwater system. That's important for the council to ensure that there's no flash flooding downstream from the new development. Infiltration, if the grounds are able to accept the water, this is sandy soil. So Australia is full of coastal regions. So anywhere along the coast with sand, you can put the water back into discharge the water back into the ground, replenish the groundwater, and with the scarce source of water these days, and during droughts, we want to retain the water and reuse it. So they are a lot more popular now, especially in new developments, to hold the water, either just to irrigate the landscaping or for sports fields. So just reusing the water is becoming very important in this day and age.
Thank you for that. And Darren, we've just got an alarm about to go off. So could I ask you to just go through poll question 3 and 4 with our audience? Thank you.
Poll question 3, in your current or past roles, what type of underground stormwater tank have you specified? So there's 6 options here. First option, precast concrete, single piece, or a precast concrete modular multi-part, cast in situ concrete, plastic geocellular, plastic crates, or modular arches. So it looks like there's some issues on the EA side. They've had an alarm, Amanda said. I haven't been able to see, I suppose, the polling answers. Oh, here we go. It's up on the screen now. So yeah, look, Anthony spoke about in his presentation that cast in situ concrete is probably the most common with engineers and designers, as they can design it hydraulically and structurally. Plastic crates, plastic geocellular are up there, and these are due to the cost, I suppose, when you're comparing it to concrete. They're a lot more cost effective. Precast concrete, other options. So there is a lot of different options, and it really depends on how, based on your project brief, your designer's brief, what your client wants, and your constraints on site, I suppose, is on what product you pick to design and specify and in the end install.
Thank you for that. Are we up to question 4, Darren?
Yes, we are.
Okay, so question 4, which is our final question. What support do you value the most from a tank manufacturer? Ranking 1 to 4, with 1 being most common. And the first option is 2D and 3D drawings and product data sheets, project-specific support to size and configure a tank, project-specific structural calculations to verify a tank's strength, or personalised support from a technical representative. Please vote now. So, Darren, do you want to comment on our final polling question?
Thank you everyone for participating in the poll. I suppose the poll results are very interesting for us. In regards to support this question, it really helps us develop what support we can provide as a manufacturer to the engineering and design community. Obviously, 2D and 3D drawings of the products and data sheets we can supply to help you, specify and draw the tank. Project to configure and size the tank, we've got a configurator program to help you hydraulically size. So you've got a volume of the tank, we can size up the tank for you using our configurer online. And even you can even check with your the structural design based on a few inputs you put into our structural design calculator. You can be sure it'll provide answers, I suppose, to the strength and durability of the tank and how much deflection the tank will have over time. This information we can provide with outputs that contain all the information, calculations, our factors of safety we applied, so you can follow our calculations to arrive at our conclusion and results of that. So yeah, we like to keep on evolving our support. So yeah, please get online and have a look at the online support we have at the moment. But we keep on helping, I suppose, the design community with further development in this area.
Thank you, Darren. And thank you to everybody for sharing in the poll. We'll now move on to the Q&A, and if you could please ask us speakers questions via the YouTube chat box and whom your question is directed to. And thank you to everyone who put forward a question whilst registering for this webinar. And we might start, Darren, with you. And we've had a question that came in from Sean. And Sean is watching in Queensland. Good afternoon to you. It is just afternoon. Asking you, Darren, acceptance from councils under roads or in verges?
Yes, thanks, Sean, for the question. That's a good question. I suppose councils need to ensure their infrastructure is there for a long time. So they want structures that, I suppose, under roads or in verges to be strong enough to cater for that. With the ACCO storm bricks, we can provide information on all our testing and how strong our product is. Definitely in verges, not a problem to install storm bricks. We have had a lot of installations in these kind of areas. We've seen a lot of specification coming down from the Mornington Peninsula down in Victoria, where the road drainage actually gets captured along the gutter into the curb inlet and straight into it and piped into a storm bricks that is on the verge, and sometimes it's even designed halfway under the curb and gutter onto the road. Look, ACCO storm bricks is can be installed under residential roads, but you wouldn't want to install these type of plastic geocellular tanks under major roads, highways, freeways. It's just not there to designed to take consistent long-term traffic, but just for the occasional traffic in residential roads that just rarely trafficked, they're being installed. So we've seen a lot of these in Newcastle, in New South Wales, in the verges, in the medians, to capture this water and just to infiltrate it back into the ground. So residential roads shouldn't be a problem, but you wouldn't be putting these under major roads.
Thank you. Thanks, Darren. Anthony, we've had a question that's come in from Caroline, and Caroline's watching in New South Wales. And Caroline is asking you, Anthony, and you may also want to comment, Kate, are confined spaces always a consideration with underground on-site detection?
Yes, well, thank you, Caroline, for your question. For our concrete tanks, the short answer is yes, always yes. Both precast and in situ tanks need to be accessible for both people and equipment, particularly in cases where you have hydraulic assets, including orifice plates and weirs, as well as treatment devices within your tank. People must be able to get into each and every chamber in order to make emergency repairs or do scheduled maintenance, those sorts of things. There are a couple of key considerations here when you're actually thinking about confined space access. The first is you must have access points at regular intervals. This allows people to access the tank in an emergency. If you have an underground tank, there are occasions where you can have pockets of gas that may actually render people doing maintenance unconscious, and so you need to be able to rescue them. And you don't want to be too far from an access point in that case. So the distance to the nearest exit is always a consideration that needs to be made. In addition to this, you need to make sure that every chamber of your tank, if you have multiple chambers, is accessible by its own access point. We have had a couple of cases where you have an internal wall that's not the full height of the tank, where you can't actually fit a person or the equipment that they're carrying over the wall. So it is important to make sure that you are considering these aspects when you're designing your tanks for confined access.
Thank you. And do you want to comment, Kate?
Yeah, thank you. And thanks, Anthony, for the insight on concrete tanks. I guess what I just want to add to that is really any confined space is a risk that's avoidable by using technology. So what we sometimes see in concrete tanks in the field is also leftover formwork that's there from the installation period. So you have that to kind of work around as well. And yeah, like I mentioned in my presentation, having accessible open cell structures like storm bricks and using technology to be able to inspect and maintain them is a kind of a modern alternative to using actually physically sending somebody into a tank to maintain it.
Thank you, Kate. Questions come in for Anthony from Lucas, and Lucas is watching in Victoria. It's a great question asking you, Anthony, do we still rely on rational method peak flow differences to size OSD systems, or should we be utilising full hydrographs for more accurate detention storage? Have you seen major sizing differences between the two methods? Thanks, Anthony.
Thank you, Lucas, for your question. I think this is a great question. Just to touch on it briefly, the rational method is essentially the use of first principles calculation to figure out how much stormwater you need to store in your tank, whereas hydrographs or runoff routing methods are effectively software-based. And these do a lot more to consider the storage and the actual volumes of water that might be moving around your tank during any specific storm event. In most applications, in my experience, there is a substantial difference between the results that you'll get for your detention size with the rational method and using a runoff routing software. The difference can be up to around 20%. When you are looking to optimize the footprint of your site, that can be a major advantage, and it can result in excellent outcomes for your stakeholders. A couple of things to consider. There are still some councils who require the use of a rational method or an equivalent in order to size your detention tanks, and they won't accept the results of software outputs in this case. However, if you have the freedom to use your engineering judgment to design a detention tank, I would always recommend putting the rational method away for now and using software to determine what size your tank should be.
Thanks for that, Anthony. Over to you, Darren. A question from Bayani, who is watching in the ACT, asking you, Darren, can these structures be one of many solutions to flooding?
Thanks, Bayani, for your question. Well, obviously, stormwater tanks, whether they be detention, infiltration, especially detention tanks, they're designed to mitigate flash flooding downstream. So, of course, for your short-term intense storms, that's what the OSD tank is designed to suppose slow down the peak runoff from your site, therefore not flooding downstream infrastructure. Now, look, they're therefore just short, intense storms. But if you've got long, extreme rainfall periods, these kind of tanks, they will fill up pretty quickly, and they won't be able to. They'll store some water, but still you're going to get flooding, as you would, where if all the soils are saturated and your rivers are starting to flood, that's you can't control. Not a tank you can design big enough to hold that water, but definitely for short, intense storm events that pass that dump a lot of rain in a quick period of time. That's what an OSD tank is there designed to hold that water for a short period and then release it very slowly, just to ensure that downstream from that there'll be no flash flooding, or to prevent the flash flooding.
Thank you, Darren. Anthony, we've had a question from Sivaraja, watching from Victoria, asking you, what are the geotechnical or soil testings required for stormwater retention, detention, design?
Excellent. Thank you very much for your question. The answer is the same regardless of what you think the tank is actually being used for, whether that's retention, detention, or infiltration. And the answer is that the geotechnical information that you need is the same as if you were designing your structure on this site. So the information that you need for a tank is the same as what you need for a building. The key information that you're going to look for from your geotechnical engineer is the soil classification, that is its reactivity, particularly to moisture, as well as your bearing capacity. So that's reflective of the amount of load the soil can take before it will fail, as well as groundwater information. The first two are more critical for the design of the base slab, where the groundwater is actually more critical for the design of the walls, particularly if you're looking at having to deal with water ingress into your tank.
Thank you for that. Question, Darren, from Ernst, watching from Victoria as well, asking, could you elaborate, Darren, on how short-term loads, creep, and long-time deformation are accounted for in the design process of plastic modular tank systems? Thanks, Darren.
That's a good question, Ernst. Thank you for that. Look, short-term loads is very easily to test for. Most geocellular tank manufacturers will provide the short-term loads. It's very simple. You can just take your cell, take it to a test laboratory, put it under a test under compression, and see when it breaks. So that's very easy. Any of the manufacturers out there, they can provide that information. Very simple test. But what they need to also design or test for is long-term loads. Now, to test for creep loads, for creep and long-term loads, that's very expensive and a very long test. So you would have seen in Kate's presentation that we've at ACCO, we've set up our Stormbrick system, and we've put concrete blocks on top of it, and we've just measured the over time. We've tested over 10,000 hours under that test. That was shown, that was set up, and we were able to plot the deflection of the module over time. So from that, we can work out the creep of the plastic material. So creep is the plastic deforming over time under weight, constant weight. So we're able to determine that to see how strong our Stormbrick's tank is, and we've got all that data to provide if you need. So that's probably a question you should ask other geocellular tank manufacturers to provide. How we've used this, we've actually incorporated these results into our structural calculator to account for the deflection. So with the structural calculator, you can put in all the loads and what kind of soil requirements over the tank, and then with the live loads, the dead loads, we can work out the deflection of the tank based on all those test results that we've tested it to. The deflection is usually the pass-fail criteria, I suppose, unless it's very heavy loads. But the deflection of the tank, will determine. It's very important, I suppose, if there's a concrete slab on top. You can see if the tank will deflect a lot, that means you'll start seeing cracking on your concrete slab above. Asphalt, if you have an asphalt pavement on top, not as important. You won't see the cracking because it's a flexible pavement. So, yeah, look, it's very important, both the short-term loads and the long-term loads together, and in fact, the lateral loads too. So at ACCO, we've actually tested our products to lateral loads. Lateral loads will become important if it's going to be installed very deep in the ground. So if you've got a big cover, a lot of cover over the top of the tank and a very deep tank, then the bottom of the tank would be loaded a lot more than the top of the tank. So strength laterally on the bottom of the tank will become important. And even if there is a high water table, then you've got your hydrostatic pressures also on the side of the tank. So these are, I suppose, other geocellular tank manufacturers should supply all this information, especially lateral loads and long-term loads. So next time you design it, just to be sure, I'd request this kind of information from those suppliers.
Thanks, Darren. Anthony, a question's come in. Can infiltration be used as part of the solution in combination with a more conventional detention method? Thanks, Anthony.
Well, thank you very much for your question. The answer to this one is yes, but you do need a specific set of conditions in order to be able to do infiltration and detention together. As a reminder, infiltration is where we lose water into the ground, and detention is where we are losing water through a small orifice at the bottom of the tank, which goes down to council's stormwater drainage system. You can have both of these in a tank together. However, as I mentioned, infiltration tanks often have to be quite big. And if you are designing an infiltration system as part of a detention tank, which is much smaller, the infiltration component is not going to be as effective. There are a couple of things you can do about this. On sites where you have very sandy soils that can actually infiltrate water very quickly, you may actually see an advantage in being able to infiltrate the water rather than just using an orifice to discharge it. A couple of things here to bear in mind. First of all, when you're designing an infiltration tank, you are looking at ensuring that you have an infiltration of probably around the 300 millimeters per hour mark. Most detention tanks are approximately a meter to 2 meters deep, and the critical storm events mean that they will only be filled for about 5 minutes at a time. So if we're looking to deal with an amount of water that can be up to 2 meters deep that will drain in 5 or 10 minutes, you're not going to see a substantial improvement by losing 300 millimeters per hour of that water by infiltration. So you really need to be targeting sites where you have extremely high infiltration, at least in the order of 1,000 millimeters per hour or something like that, before the infiltration is actually going to be effective at improving the performance of your tank. So soils that we're looking for that can achieve that are loose sands, definitely not clay, definitely not rock. Unfortunately, for most of the east coast of Australia, we are looking at clays and rocks, but there are a couple of coastal situations where you may be able to improve on your performance by utilizing a sandy foundation. Obviously, having a sandy foundation, you have your own set of structural issues there. You may end up having quite extensive footing systems in order to utilize that infiltration. But obviously, it's a balance that can be struck. You just have to know exactly what's going on your site.
Thank you. Kate, we have a question for you asking, which maintenance problems occur most frequently? Thanks, Kate.
Thank you. I think no maintenance is the biggest maintenance issue that we're seeing. We have lots of these assets that just aren't being maintained. And perhaps it's just a bit of a lack of ongoing maintenance of that particular site, or not being able to actually access that asset as well. So I think fundamentally that's the first part of it, is that we have an asset that can be maintained, but also a bit of pre-treatment upstream of a tank as well. So something like a gross pollutant trap or something to kind of keep the worst of the sediments out of the tank.
Thank you. A question that came in is the plastic tank. Darren?
Sorry, what was the
Yeah, how does the plastic
Sorry,
tank bear the lateral loads?
Okay, yeah, thanks for the question. Yeah, how plastic tank bears the lateral loads. With the Stormbricks tank, obviously we've got the main bodies, but on the perimeter of the tank, we have side panels. So the side panels are placed against the body of the tank, and it only goes on the outside of the tank. So it leaves the open structure inside. And with that side panels, they are actually designed to bear pressure back onto the main bodies, which takes the bulk, I suppose, loads from the ground. Those side panels are also used to ease, so you can easily wrap the tank with a nice flat surface. So look, with the in Kate's presentation, you would have seen some photos, and we've actually turned the actual main body modules on the side, and we've tested it laterally. So we understand the strength of the ACO Stormbricks and the loads that it can take. And what we've, as I said in my last answers, is we've incorporated this into our structural calculator. So that structural calculator will look at the lateral loads, and that'll be just dependent on the depth of your tank and if there's any hydrostatic pressure. So that's all taken into consideration, and that's just measured up against our design or tested loads of the product.
Thank you, Darren. Thank you. And just staying with you for now, we've had a question from Adrian, watching in New South Wales, asking you, Darren, how do you incorporate water quality chambers and discharge control pits to your prefabricated system? Thanks, Darren.
Thanks, Adrian. Yeah, with geocellular tanks, as you see with all the images from Kate's presentation, that it's not a full open structure like a concrete tank that we saw in Anthony's presentation, where you can actually house all your your water quality chambers and your discharge control pits within the four walls of a concrete tank. Obviously, with geocellular tanks, you can't do that within the tank. So how we incorporate it is now upstream from the tank, you'll have all your pipes going into a pre-treatment water quality chamber. So into your GPTs, a sediment trap, silt trap, any cleaning, pre-treatment systems you put upstream, and then you pipe the cleaner water, the treated water, into the tank. That's very important to put it upstream, because the last thing you want to do is put it downstream. That means all the sediment will go into your tank, and that means it's harder to clean the actual Stormbricks tank itself or Geocellular tank itself. So you will want it upstream, where maintenance is the key, as Kate said. These got to be cleaned, the pre-treatments regularly, to ensure they function and do what they're designed to do. With your discharge control pits, once again, that'll be downstream of your tank. So you'll have a pipe going into a pit. Your pit will house the orifice plate to control the flow. The discharge pit could be a pump system if it's in a retention tank, where you'd house the pump so you can use the water for reuse.
Thank you, Darren. And this may be our final question, and I think you've touched on this in your last response, but we have had a question from Daniel asking, if a flood event has caused a milk crate system be filled with sediments, can these be cleaned out effectively, or the whole system needs to be removed and replaced with a new one? Thanks, Darren.
Yeah, that's a good question. So I suppose the geocellular system started off with milk crate systems. So it's pretty much from the video that I was in Kate's presentation, where I was assembling a crate system where you build a flat pack system, build the four walls, and then put some baffles in between and put a top. So when you put all these little crates all together, there's really no way that you can clean the sediment out. So once you put all these crates together, the sediment goes in. You're in your inlets where the sediment goes in. You can capture all sorts of things there that could start blocking up the inlet, start filling up with silt, the tank. So with the milk crate systems, it's got a limited life. That's in particular for maintenance, because you can't get access to it. So look, with the ACO Stormbricks, we've learned from that first generation type of geocellular systems where you couldn't maintain it. We've designed these pillar systems where the actual tank, you can gain access through an access chamber into the tank, and you can run your CCTV and your vacuum pumps all the way through the tank. And if it does get silted up, we can maintain those. So very important for your asset owner to consider access and maintenance, and to probably look at some new designs of geocellular systems that are out there in the market now.
Thank you, Darren. Before I thank our speakers, I'd just like to announce that we are running a competition today, which has been provided by ECHO with a prize. So if you could please share your answers to the email on the screen, there will be a gift card prize for the winner. And the question is, in less than 100 words, in what applications would you not specify concrete tanks, and why? So I encourage you all to join in. It's the season of giving coming up. Thank you. So it is all the time we have for today, and please join me once again in thanking Kate Jennings, Anthony Healy, and Darren Chan for their time and expertise. Before we wrap up, I would also like to encourage you all to complete a short feedback form, which is linked in the description box below, to help us improve and plan for future sessions as we head into the new year. I'd also like to thank Engineers Australia's industry partner, ECHO, for their ongoing support. Thank you. So thank you again for joining us, and I look forward to seeing you at our next Industry Partners event. So thank you and good afternoon.